Good afternoon, Internet. I am Matt Buyak, and in this video we'll be taking a look at the 58th problem from the Project Euler Problem Archive. Now, this problem asks a question about this peculiar arrangement of the integers that has 1 in the center, 2 to the right of that, 3 above 2, and the rest of the integers continuing in this counterclockwise ascending spiral pattern. It makes two observations. The first is that the odd squares lie along the bottom right diagonal. And the other is that the other three diagonals seem to contain an unusually high number of primes. Just considering the integers displayed here, we have 8 out of the 13 values are prime. You'll notice that it's counting 13 rather than 12, which suggests that it's including 1 in that count. So we should be sure to do that as well. In any case, the question that it asks of us is, at what point does that ratio fall below 10%? That is, as we're adding new layers to this spiral pattern, what is the side length of the square at the point when that ratio falls below 10%. And I think this problem isn't too difficult. Obviously, we'll be using our primes class. I did a whole series of videos about that, so I'll put links in the description if you're curious. Mostly, we'll just be using that for basic primality testing, checking if a particular number is prime or not. There's just a few other tricks that I'll mention before we get started. Rather than laying out this whole pattern of integers in memory in some giant two-dimensional array or something like that, we're just going to directly calculate the values for each of the corners in each layer of our pattern. Since those are the only numbers that we actually care about in any case. And the way we'll do that is to first observe that there's at least one corner in each layer that's very easy to calculate, and that's because it's an odd square. If we number the layers, starting with the center being layer 0, it's just 1, it's not really a layer, then we can use that layer number to easily calculate the corresponding odd square just by multiplying by 2, adding 1, and squaring. So we have, this is layer 0, we don't care. Layer 1 is, multiply that by 2 and add 1 gives us 3. Squaring that gives us 9. Layer 2, we have 2 times 2 plus 1 is 5. 5 squared is 25, and so on. So you can see we can very easily calculate the square in each layer. And then from that, we can calculate the other 3 corners just based on the fact that the difference between the odd square and each of the other corners is going to be the same as we step around the square. So for example, we have 25 here. Subtracting 4 gives us 21. Subtracting 4 again gives us 17, and again gives us 13. So we can start at the square and repeatedly subtract twice the layer number to get each of the other 3 corners. You'll recall that we numbered the layer, which includes 10 through 25, as layer 2. So double that is 4, and so that's the amount that we're going to need to subtract to get each of the corners. Just to check to make sure that that works in all cases, consider layer 3. Our difference is going to be 6. We're starting at 49. Minus 6 is 43. Minus 6 again is 37. And again is 31. And so that's going to be our process for calculating each of the other 3 corners. Note that we don't need to do primality testing on the odd square because it's a square. We know it has a divisor. And so with all that in mind, let's get into it. As usual, we will copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. We will include our primes class, and open our makefile to link in our number theory library. Let's actually open up that primes class just for those of you who haven't had a chance to take a look at that. Here's the header file, and mostly we're just going to be concerned with this method here is prime, which we'll use to do our prime testing. Okay, so we're going to need to count the number of corners that we've looked at and the number of primes that we've found, so we can, after each loop, determine whether the ratio has fallen below 10% or not. So we'll say int num corners. We'll start that off as 1. You'll recall that this center counts as a corner for our purposes. And then num primes is going to start off at 0. But this poses us a little bit of a conundrum because right now the ratio of primes to corners is 0%. And so if we were to check at this point whether we are at or below 10%, we would already have met the conditions for termination. And so what we want to do is use a do while loop. So we're going to say do, and then down here we'll say while 10 times num primes is greater than or equal to num corners. Okay. We will also need to keep track of the current layer that we're on. So we'll say int n is equal to 1. That is, we're going to start off by adding the first layer, which is 2 through 9. And so down at the bottom of the loop, we'll have to remember to increment n. Okay. So now let's calculate that odd square. You'll recall that we take n and multiply it by 2, add 1, and square it. So let's say int sqrt, so that's going to be square root, and that's just going to be 2 times n plus 1. And then we'll say int odd square is equal to square root times square root. And then we'll say corners. There are going to be 3 other corners that we consider, and they are going to be odd square minus 2n. This isn't algebra. We have to actually put operators in here. Odd square minus 4 times n, and odd square minus 6 times n. Okay, and we'll say for int I is 0 up to 3, increment I, and we'll say if, yes, we need an instance of our primes class. I always seem to forget this, primes p. And we'll say if p dot is prime corners I, then plus plus num primes. And after each layer that we add, we're going to say num corners plus equals 4. Okay, that should be just about everything. One thing that might be worth doing is if we can actually check to see that our code is working as intended. So let's start off by actually changing our termination condition for a moment and say n is less than 4. So we'll consider layer 1, 2, and 3 just as in the problem description here. And in here we'll say printf, and we'll say layer %d has corner %d. So that's going to be n and corner I. It's often good to do this kind of sanity check just to make sure that all the algebra and calculation that you've done in your head or maybe on a piece of scratch paper actually plays out the way you expected. So let's switch back to our shell and make. It seems to be a little bit unhappy. Yes, it's corners, not a single corner. Okay, so we see that in the first layer, our corners are 7, 5, and 3. That is correct. Then we see 13, 17, 21. 13, 17, 21. And then 31, 37, 43. And we have 31, 37, 43. Okay, it looks like our code has passed our sanity check. So let's delete our printf there and go back down here and restore our original termination condition. And recall that the point at which, or the actual final answer that we're being asked for is the side length of the side that adds the layer that causes us to drop below 10% for our ratio. So how do we come up with that? Well, let's consider the outermost shell of the example here, and that's, as you recall, layer 3, and there are 7 elements along the side of layer 3. And so we're going to get that by taking the layer number, multiplying by 2, and add 1. Similarly, you can see that there are 5 elements along the edge of layer 2 and 3 along the edge of layer 1. One point of caution is that we've already incremented n at this point in preparation for adding the next layer. And so we actually somewhat awkwardly need to then decrement n and say printf solution is equal to solution, 2 times n plus 1. Alternatively, what we could do is 2 times n minus 1 and get rid of this minus n here. That should give us the same thing. Going back to this example, after adding the third layer, we will have incremented n to be 4. But then if we multiply 4 by 2 and subtract 1, then we get 7 as we expect. So that should be correct. Let's go back to our shell, make, and run. Thinking that we may be in a little bit of an infinite loop. Let's take a look at our code and see if there are any obvious mistakes here. 10 times num primes. One thing that might give us some inkling as to what's going on, let's just say printf num primes equals %d, num corners equals %d. Looks like it actually is possibly making progress. I'm a little surprised that it's progressing as slow as it is. It is remaining stubbornly just above the threshold, it seems. I wonder if our primes class is struggling. Hello, future Matt here. Yes, past Matt. It turns out that's exactly what's happening. Unfortunately, our primes class is kind of garbage when it comes to doing prime testing on very large numbers. And this isn't even the first time we run into this issue. Just a few weeks ago, when we were doing problem number 41, we had the same problem, and we had to write this bit of code here, is large prime, to kind of work around the issue. And in just a moment, I'll get to why exactly our primes class struggles so much. But let's see what happens if we take this code and just throw it into our current solution and see what happens. So we'll just paste that right in here. Note that this takes an instance of our primes class and also the number that we are testing. So we'll go down here. And instead of saying P is prime, we'll say is large prime P, and switch back to our shell and make and run, and it's done. So much faster. Okay, so why is it that our primes class is so bad? Well, the issue is that when we ask our primes class to test a number to see if it's prime, if it doesn't already have the primality for that number cached, it will generate all the primes up to and possibly including that number to see if it's prime or not. But there's a much more efficient way of doing primality testing, and you can see it here. We only need to test up to the square root of the number in question, not up to the number itself. So why don't we just take this code and slam it into our primes class and call it a day? Well, there are a couple reasons. One is that our primes class isn't just used for primality testing. When we generate primes, we're getting a lot of information that helps us do things like factoring large numbers. Obviously, that doesn't help us at all with this problem, but if we were to lose that information, there might be some other cases that wouldn't be as efficient as they are now. The other problem is I'm concerned about certain pathological use cases where perhaps we are doing a lot of primality testing in the range of, high hundreds of thousands, low millions, something in that range. Normally, with the current arrangement, we would just generate all the primes up to that point, and our primes class is actually pretty good at quickly generating all primes less than 1 million. And once it's done that, we have those results. They're cached. And so if we do primes testing in the low millions or high hundreds of thousands, those are going to be very fast because we can get the results immediately from our cache. But if we get rid of that caching mechanism, or rather if we stop generating primes all the way up to the number in question, then we're going to have to be doing this method every single time, which is not free. And certainly in the use cases we have for problem number 41 and for this problem, this method is faster. But it may not be faster in all cases. And so I don't want to just impulsively replace our current implementation with this implementation. Definitely we don't want to get burned by this again. We've already been burned by it twice. And so we do want to come up with some kind of better approach. And maybe there's some kind of hybrid arrangement where we generate some additional primes that we hadn't already generated, and then also use this method if we need to. Certainly we're talking about something more sophisticated than just replacing our current implementation with this code here. One possibility is that we might look into doing some more sophisticated methods than we've used up to this point. There are ways of doing prime testing for very, very large numbers that are way more efficient than anything I've implemented in our primes class. And so maybe that might be a possibility. I expect that at some point in the video there will be another at some point in the future, there will be another video on our primes class where I will let you know what I've decided. But in any case, we have a solution to this problem at the moment. And so going back to our shell, that's going to be 26,241. Let's go back to our browser and go to the archives and sign in. And go back to our problem. And we see that it does, in fact, match our solution. So thank you very much, as always, for joining me in this video. In the next video, we will either be tackling problem number 59, or I might finally have that video for problem 54 done, in which case you can look forward to that.